So it's my great pleasure to introduce the last speaker of the second day of the workshop. So Professor Suvrajeet Sen, who is a professor of industrial and systems engineering at the Viterbi School of Engineering at USC. So Professor Sen is a very well-known researcher in the field of stochastic optimization and optimization under uncertainty more broadly. He has received multiple awards, among them the Inform's Distinguished Service Award in 2017. His research interests are not only in optimization, but also in the modeling of complex systems. For example, electricity grids and transportation systems. And overall, he's one of the leaders in the effort to develop efficient optimization methods for a very large-scale stochastic model. So we will have a two-part presentation today. The first one that deals more with integer decision variables in optimization problems under uncertainty. And the second part, which was the presentation that was in the program, so a comparison between SDDP and SDLP methods. So Suvrajeet, you have the floor.
So first off, I have to congratulate the organizers at a tremendous job that they have been able to overcome COVID, etc., to put together a fantastic set of talks. It's quite a testament to your willingness to navigate difficult problems. But I suspect that everyone who's working in problems under uncertainty is familiar with difficulties of such magnitude, and so we all owe you a big thank you from this community. Um, all right, so let me start with this added, the added part of this talk, which I'll go first because it is actually something that many of you encounter pretty regularly. So I figured I'd start with this simpler problem, which is uh, at least conceptually simpler, but not actually, because they're very large scale facility location problems. And uh, the work here is essentially the work of my PhD student, Jajun Shu. I am fortunate to have such terrific people to work with. So I have to thank Jajun, as well as my next co-author, Harsha. Let's start with this problem. So let's take a look at something like LA. And LA is such a large city. It has 157 zip codes. And in each zip code, you have a large number of customers. And so when you're trying to locate new warehouses and that kind of facility, then it is not simply the fact that you don't know how the patterns are going to change, but the number of combinations of these patterns can be mind boggling because if you talk about each zip code and the zip codes are growing at different rates and so on, and you don't know what those rates are, this is problems of astronomical size. And so you'll see what I mean when I say astronomical size in a minute. But essentially, if you take a look at the particular geography, there is enormous opportunity to try to use stochastic optimization. Um, and while there is a chance to use it, it probably doesn't scale so far as we can tell. So, how do we know that we're solving a problem that is relevant to the situation that we're facing? And by that, I mean we ought to be able to give some bounds about where how good a solution we're getting, if we're getting anything at all. And so I'm showing you these maps just to set the context that these are going to be very humongous problems. And now the question is, suppose we do sample averaging. Okay. Now the sample averaging problems, I, many of you out there are much more adept at using sample averaging than I am. And but the point is that once you solve a sample averaged problem, very often I find in many papers that the focus is on the optimization, but not on necessarily telling you how good a solution you have. There are people that do that, of course. It's not like everybody just puts up the algorithm. But most of the emphasis in our world, in stochastic programming world, has been the focus on the algorithm, not so much on how good a solution. Of course, there are exceptions. People like Guzain, Dave, and a whole bunch of others have been doing this for many, many years. So it's not like no one does it, but the the proportion of the community that uses, not this community, not just the research community, but people that are using, there's a whole host of users out there today of stochastic programming, and most of them think of stochastic programming as the Danzig version of 1955, where you set up a finite number of scenarios, solve that problem, and you're done. The fact is, on this kind of a problem, there is no chance of solving to any degree of accuracy. And so you have to approximate. And then there are different types of approximations you can make. And then, depending on the approximations, what is the quality of the solution that you're getting? That is going to be the focus of what we're trying to do here. Okay. And so, since I just wanted to make sure that people know that there's a lot of variability. I'm going to skip that because everybody buys the variability part. So because I'm going to add a few things here. So um, I'll skip, how we create these distributions, etc. But you can tell that there is a fair amount of infrastructure that goes into creating these things. And this is all quite common. So let me just go straight to the facility location problem. And in this problem, there are, as in any uh, two-stage type problem, there's going to be some variables which are the location variables, and then how you service from those locations to facilities, from facilities to demand centers. And those variables are usually the second stage variables. So let me just put up this location problem. And so the first stage is binary. The second stage is also binary, but the second stage is essentially a network flow type problem. So you can solve it by some linear approximations. But the first stage still remains uh, a discrete optimization problem. And so in a problem like this, when the demands are when the size of these problems are enormous, then how do we go about assessing whether we have a reasonable solution? So one thing that we have found useful is the notion of replication. This notion of replication means that since you can't clearly put all of the possible realizations into one particular model formulation, we can do SAA, but we will replicate each of the SAAs. So then what this means is that there is some sort of a true problem, and then the true problem, we sample from the true problem, create some replications. And now for each replication, we have some MIP solver, some Bender's type algorithm that will solve that in parallel. And now at the end of this, we're going to try to figure out what decision do we need to recommend. So when we replicate, of course, we get usually different solutions. And what should we do once we get these different solutions? The standard recommendation is to now take each of those distinct solutions that you get and run, fix those decisions, run Monte Carlo, get some estimates of the objective, and then from that, choose the one that has the most promise, let's say. Okay. So that's the standard MO that people follow. Um, in in my view, that MO uh, just doesn't rise to the amount of work that has gone in to solving these problems, because all it does is give you alternative uh, decisions, and then you're enumerating, and then you're not enumerating, you're looking at uh, the values that you get. One thing that we have found useful for stochastic LPs is that, so, oh, I did want to mention that for those of you that were at Jim's tutorial, you can use all of the methods that he was talking about to solve each of those problems. Okay. And so we assume that you can do that. And now what I want to do is to give you a little background. Some of you may already know all of this, but I figured to get us all on the same page, there is this idea of compromise decisions in stochastic LPs. And the compromise decision on stochastic LPs works in the following way. So let's take, we do the same ensemble LPs, and then what we will do is solve it in some fashion. Okay. What I do is used our version of stochastic decomposition, which is a regularized sampling version of Bender's. And then we assess for each of the replications, we assess some values. But most importantly, what we want is this notion of a compromise solution, which is the following. We create what we call a grand mean value function, because from each replication, what we obtain is a terminal approximation of the value functions. So for each replication, we take those grand mean value functions and we optimize that grand mean value function, which we call the compromise decision. Okay. And we then take that compromise decision and compare it with the sample average among all the replications. Now, these are convex problems, so I can show that X bar, which is a sample average, is also feasible. So now what we do is to test whether X bar and XC are close enough together. If they're close enough, then we say we're happy. If they're not close enough, then we need to do more sampling. Okay. And here's the point that I want to make here, that if I solve a sampled problem with, let's say, loose tolerance, I solve the sampled problem using whatever algorithm you want, you'll get different solutions. So if you take a look at these red dots, there are some red dots here. And if you take a look at these red dots are values that we computed after solving these 30 replications. And you see that there is a fair amount of variability going from approximately 10.1 to approximately 10.45. Okay, so there's a fair amount of variability. And this is because we didn't run it with very tight tolerance. It says loose tolerance here on the reds. And then we did similar things with some slightly more stringent stopping. It gets a little less variability. And then when we go with a much tighter, we get again variability. Again, the variability is reducing as you would expect. Okay. So the question is suppose I were to just run one replication, I could come up with a similar solution regardless of the tolerance from any one of these runs, right? So my decision values, my objective function values could be in this range for all of those three runs, even though one says I'm loose, another says I'm nominal, and the last one says I'm tight. I could come up with, so if I just run it once, that doesn't really tell me a whole lot. So that's why we run multiples. And then my compromise decision is something that is, to me, quite eye opening. And that's the following. If I take all of these solutions and I run my compromise decision, what that means is that for every red dot, I have an approximate value function that came out of the solve. And now I average those and I optimize with that averaged function. Guess what happens? When I optimize that averaged function, I get a value that is better than all of the others here. Not only all of the others here, but also all of the others in the greens and the blues. I get this red line here. Okay. What has happened here is what in machine learning they would call bagging, which is bootstrap aggregating. So we're aggregating the value functions into one and then optimizing that value function. And that value function then gives me a much better decision. And its value is now, let's see, here the best that I got was 10.1. This is somewhere near 9.95, let's say, approximately. If I do the same thing with the greens, I get a better value again. If I do the same thing with the blue, I get a better value again. You can see what's going on here, that these aggregated problems, the objective function is getting you much closer to the optimal value. And this, this level of this second stage problem, not second stage problem, this sort of, uh, this is a meta algorithm, so to speak. So you're taking the aggregation of the value functions and then using them to create new solutions. And this is what we call a compromise decision. What I wanted to do was to see whether we could do a compromise decision for these facility location problems that are that large. Okay. The difficulty is that we needed to use some X bar in the case of in the case of the LPs, we needed the sample average of the solutions also to compare. And instead of, and we can't quite do that because the averaging in the integer case won't really work. And so so this part here is, I'm gonna, so just a summary here, that the compromise decisions are better than any of the ones that you run into. Okay, so this is a takeaway that I hope to leave with you, that the compromise decisions are better than every individual decision of the replications in such examples. Okay, let me now show you, at least intuitively, you can see that when you take one replication, its expected value is not going to be as good as the lower bound estimate coming from the compromise, which is also going to be less than or equal to the optimal value anyway. But this reduction in bias is quite significant, as you saw. The reduction in bias is significant. The reduction in variability is also significant. They're both reduced. And that's sort of the key point that I want to make. Now, let me go to the facility location problem. Here, instead of using the instead of using the bagging directly, what we do is use some kernels. This morning, there was someone mentioning, hey, when are they going to bring kernels into stochastic programming? Well, here we are. Okay. So what we do is essentially uh, solve multiple replications, get these solutions, and these are M replications. So M is 30. And now we create this gram matrix, which is this inner product between the different solutions. So x hat I and x hat j are different solutions that came from the runs. And we can define a centroid of this in just the standard way. And then find the bagging solution. The bagging solution would be one which is the best and closest to the average value of, so the average value, so this quantity itself is not calculated. What we calculate are these gram matrix coefficients, because you may not really be able to compute with the fees, but you can compute these inner products. And because you can do that, you can calculate this x sub b and then x super b. And then the test is to check whether this x super b equals the value of the decision that comes out of x super c, which is if you're using benders, right? If you're doing benders, then for each replication, you've created your own value function approximations from benders in the first stage. So you can do the same thing again in the first stage and create X super C. And now you check whether X super C and the bagging solution are close together. And if they are, then you're golden. So let me take a few, let me not give all these theoretical things so far. All I want to do is to end this talk on this note of solving the compromise problem using the same kind of approximations that you did for all of the benders solves. You collect them up together, you solve that problem, and that solution is what we will call X super C. And then you take X super C and compare with the bagging solution. So let me show you what happens in some of these problems. This is just a nice looking picture. You know, the students love graphics and they do this for me. I have no idea what it's trying to say, but it's just trying to give an impression that there's a lot of uncertainty, and these are all the different realizations that are coming about. The random demand is this blue dots that are changing in size. And then the potential facilities are these red facilities. The open ones that are already available are the yellow facilities. And so what is the solution that comes out of this? We'll solve that problem. And in these problems, you can see how large the number of random elements are: 4,000, 7,000, 9,000. These are truly astronomical, because these random elements are themselves going to be having all these different scenarios. And then these facility location problems come about in different types of applications. And for each of those, there are different ways to approximate the, the, the location of the demand. In some cases, you create centroid based on geometry. Other cases, you just sample. Third case, you do some weighted centers. These are these are guided by applications. I won't go into that, but what I want you to see is the values that you get. I mean, for a problem of this size, take a look at the difference between the lower bound confidence interval and the upper bound confidence intervals for each of these different types of applications. Take a look at this: 30, 30, 39 to 30, 40, 30, 49 to 30, 49. So in terms of the upper and lower bound confidence intervals, it is relatively reasonable that you're getting lower bound confidence intervals and upper bound confidence intervals on the same magnitude. Okay, this gives you a sense of how good a solution you may be getting. Your upper and lower bound intervals are really close together, okay? And the various quantities are computed according to this kind of a rule, which is in this case, you count how many times each solution showed up, and the one with the most is the one that gets the nod. And in this case, you count how many times each decision showed up. That itself is a kernel, the counting of how many times each decision showed up. In terms of the standard deviations, you can see that these are pretty low. And so I'm going to stop at that. I've taken 25 minutes here. So if you have any questions about this part, maybe you can ask those questions now, because then we can shift in the next few minutes. I'll shift over to the other topic, which will have a whole different set of questions. So I'm happy to answer any questions that you might have.
So we can take 5 minutes to ask the questions on the first part of the talk. So again, anyone questions? Either raise your hand or. So maybe I have one.
Okay.
So just in terms of qualifying what the compromise solution is. So the compromise solution would be the one which is simultaneously closest to all of the, let's say, optimal values obtained with, let's say, each separate sample. Would that be correct? Or maybe I'm not.
Yeah, no, it's not quite that, because what we do is we take the value functions that came out. When you solve the vendor's problems, you get those cuts, right? Mm-hmm. So every replication has its own set of cuts.
Okay.
Now you take those whole set of cuts and create an averaging problem.
Okay.
And you solve that averaging problem.
Okay.
So that gives you the compromise solution among all of these.
Okay, perfect.
Thank you for asking.
So,
anyone else?
Anyone else?
Okay. So
no
if
questions,
not,
we can switch to the next.
I'll switch to the other, and I'll do a stop share. And let me end this show. Okay. And now, okay, here we go on. So this one is again work with my co-author Harsha Ganga Manawar. And in this talk, we're now going to switch to multi-stage stochastic programming, but we're going to talk about an alternative that we're calling stochastic dynamic linear programming, and want to compare it with stochastic dual. Yes.
I think the share screen, so it's not the PDF is not showing.
Oh, really? Oh.
The full screen.
Oh, okay. So let me do a stop share again. And I don't know what's going on then. So let's see what happens. I don't understand this because the Adobe is showing up here. And I go to the view. I, hmm. Let me see. Not this. Your screen sharing. Let me do one more time here, like someone
Perfect.
suggested. There's the shield here. What about the shield? Let me do a stop share and go to the shield. Okay, so there are uh, some assumptions of stochastic dynamic linear programming. And let me explain quickly what the purpose of this is. The purpose is that, as in the previous talk, when we solve a sample average approximate problem, we really need to figure out how good a solution we're getting. Okay. And in SDDP, it's even harder because we're looking at multi-stage problems. And so it's the same thing. So you can think of the difficulties as being the following. What, after all, is SDDP? It is a multi-stage extension of the two-stage Bender's method. Whatever you can do with Bender's in two-stage, SDDP lets you do in multi-stage. Okay. And so um, what we wanted to do was to figure out a way in which we took other algorithms. So, for instance, there are deterministic proximal point methods. There are stochastic proximal point methods. And one stochastic proximal point method is this stochastic decomposition algorithm for two-stage problems. So what we decided to do is to see what would be the benefit of having these other types of algorithm extended to a multi-stage setting. Okay. The difference is in basically the convergence analysis and the algorithm itself, of course, but the convergence analysis is not based on the Bender's philosophy of saying that at the end there are only finitely many bases, and the finitely many bases can only appear once, and once they appear, they're not going to repeat themselves. And that's the convergence proof of Bender's. That remains the convergence proof essentially of SDDP. On the other hand, when you look at something like proximal point methods, the convergence proofs rely on showing that asymptotically your gradients your gradients vanish, which is a different algorithmic philosophy than generating all possible cuts. And so we wanted to do it in those terms because so that's why the name SDLP is Stochastic Dynamic Linear Programming, because the arguments of convergence are not based on the finiteness of the bases. It is important to have finite number of bases. So we're not saying it is not important. It is important to have that, but the convergence proof ultimately relies on showing that the gradients vanish. And so the stochastic approximation of the gradients also will vanish in this particular case. So that's the essential goal of what we're trying to accomplish here. Okay. There are a few other things that we want to accomplish along the way, and that is to be able to create policies. Okay, we want to be able to create a policy so that if there are scenarios that show up that you didn't see in the beginning, you should be able to react to those scenarios by using a policy that was generated by your stochastic programming solver. Okay, so these are, I guess, our two major goals. So let me get going here to the next slide. And so the model itself is also patterned after some dynamic system literature. So we have a finite discrete time horizon. And in this time horizon, the state variable has two components to it. One is an endogenous state, which is the X state variables in dynamic systems. And then there is an exogenous state, which you don't control. So the state variables under control are these X's. The state variables that you have no control over are the omegas. Okay. And now what we will do is for each stage, we will have this decision U. Okay. And the structure of this will essentially be the same as a dynamic system in which there is uncertainty and the states evolve according to the trajectories that are being shown by the omegas. Okay, so the state transition happens in this way: xt plus 1 is equal to some linear transformations here, affine as such. And these x's are random because even after you observe the xt and you fix the ut, there is a, b, and little a, which are random. So in so we can show that classical two-stage is in this fashion, autoregressive processes are of this nature. And so there are many advantages to putting this in the dynamic systems framework. For instance, for those of you that love MATLAB, for instance, MATLAB has its dynamic systems set of libraries, and one could actually program these things in MATLAB as well. All right. So let's go forward in what the problems look like. So every time stage t has a two-stage problem of this nature, where you have the current and the future. The future is right here. This is a future problem where the choice will be u. And then um, we assume the same things as we assume in many of SDDP, as well as uh, the um, two-stage algorithms, which is fixed recourse. So the DT is not affected by the exogenous state. Okay. Now, the only multi-stage algorithm that a specialized multi-stage algorithm that allows no fixed recourse is PH. PH is rather general in that sense. Okay. But we require the D's to be fixed. And so the assumptions that we will impose are somewhat minimal, but for the true believer in stochastic processes, this finite support may not be as inviting, but we've kept it finite just so that we can track these things in on machines. Um, the stochastic processes are the stage-wise independent. And when it is not stage-wise independent, there are schemes. I'll mention some of those schemes that are similar to what we're talking about, this SDLP. But we wanted to make as close a match to SDDP as possible without losing our goals, which is to see whether we can create an algorithm which doesn't depend on showing that all bases have been seen. All right. So the algorithm itself looks like this. Um, we're at any given stage, we have an approximation with n scenarios. And these n scenarios for SDDP stays fixed. When we do sequential approximations, though, these sample sizes grow. And the growth in the sample sizes is essentially, uh, it helps you in two ways. One is it makes the algorithm recognize that a fixed set of scenarios is not necessarily the ground truth. Okay, there is some benefit to letting the algorithm know that this this set of scenarios is not necessarily the ground truth, because what happens otherwise is that you can overtrain, overfit to that set of scenarios instead of being a little more flexible. So in the sequential sampling, we let the sample size grow. In our case, we just said that we'll grow it by one, but you don't have to grow it by one. You can grow it by however many you want. Okay, so sample size growth can be another parameter that you experiment with. We haven't done that. All right, so the difference is that the K keeps changing, this K keeps changing with the iterations, all right? And so you could have a situation where um, the one of the other things that I want to point out is that by letting the sampling be internal to the process, we do not need to know the probabilities exactly. We can run an oracle that creates samples as needed, and you just keep going. Okay. And what the computer does is the algorithm keeps track of how many times nodes show up. So, for instance, in this picture, you can see all these ones sitting at these nodes, right? So, in the first iteration, you had this path show up. Okay, so each node got its one. In the next iteration, you had another path show up. Okay, third iteration. Now, you see, here now, this node is being seen a second time. So you see one ones, but this node has been seen a second time. So now it gets to say, I'm counting that again. Same with this node. So as you run the algorithm, you will see that these nodes pick up how many times they're being visited. And from there, we infer what their probabilities are going to be. And as the algorithm proceeds, these particular counts will tell us how to weight the objective function values. Okay. And so uh, the one of the major benefits of this is that you don't need to have a, a probability estimate to start with. As long as you have an oracle that creates sample paths, you can hook it up with this kind of an algorithm, and you should be able to run it until it settles down. Okay, so let's go forward. So the probabilities are getting estimated in this fashion. Of course, there are other ways to estimate these probabilities. For instance, one of my students is looking at non-parametric estimation of these kinds of probabilities. So we can advance it to beyond just um, these frequencies. But anyway, the objective function gets approximated in this fashion. And so I want to connect this up with our literature, just so you can see what's going on. I'm going to go in a little bit of a hurry here now, but I have only 10 more minutes. So I want to finish up in time. Um, the uh, the source of all this, of course, is Bender's, so that's highlighted, as well as L-shaped. The Bender's guys came from the IP world. L-shaped comes from the SP world. Both of these are very similar in spirit, and these give rise to what we call stochastic decomposition. And then these also give rise to SDDP, which is down here. There are other related differences. There is Burge's nested benders, And the difference between nested benders and this benders of SDDP is that the advantage of independence is being utilized in SDDP, whereas Birch and his nested benders didn't assume independence. And so there is uh, so and in the same vein, this nested benders has its sampling version, which we call multi-stage SD, and this also appeared in SciOpt 2014. So that's about 6 years, 7 years ago. Um, so these are parallel developments. On the right side are the stochastic algorithms. On the left side are more or less deterministic algorithms, although the stochastic dual dynamic programming allows some sampling, and so does abridged nested benders. These ones that allow sampling only sample on the way forward. They do not sample on the way back. Okay, sampling on the way forward doesn't change the proofs. Sampling on the way back changes the proofs because your approximations are random. Approximations in all of the ones on the left-hand side are deterministic approximations. The approximations on the right-hand side of this picture are all stochastic approximations. I mean, randomized approximations. So that's the basic difference between these two algorithms. All right, so um, let me go forward. I don't think I have, let me show you quickly what we do. As in SDDP, we solve a master. The forward recursion is, instead of doing uh, all of the paths, we do sample the path, which SDDP does as well. Um, the probability estimates are something that we update. Probability estimates in SDDP are fixed, given, and simulate along the sample path. All right. So there is an additional wrinkle that we use, and the additional wrinkle is this prox operator. This prox operator is actually quite critical because it controls how much your decisions can change. And if your decisions are such that the objective function value is not improving, then you can increase the value of this this prox parameter. And when you increase the value of the prox parameter, it's something like a trust region method, which means it's holding you back and not letting you take long steps. If you're making progress, then you allow the parameter to reduce so that it doesn't control so much. Okay, so this incumbent solution is the same thing as what in non-smooth optimization they call trial points. So we call them incumbent solutions because the origins of this happened in an election year where we were talking about incumbents and candidates. And so that's where this terminology came from. The incumbent is the one that is currently the best seen so far. Candidate is the solution to this problem. So this UK0 is the candidate solution to this problem. If it improves, then we swap the candidate and make it the incumbent. So that's the basic scheme. Since I'm running out of time, I'm just going to show you what we do quickly in picture form. We create a prediction pass, and the prediction pass identifies for us an incumbent. So one pass we create is the prediction pass. The other one is the optimization pass. The optimization pass goes across and finds the next possible solution. The prediction pass is intended to find these incumbent states. After we do this passing, I'm going to skip this. So let me go to the backward recursion now. The backward recursion comes backwards now. We only go along the path that was sampled in the forward pass. This is the difference with SDDP. SDDP, you essentially take the entire tree and come back. Here, we'll just do it along one path. And so this back and forth is happening only along one path. The reason for that is that over time, when the problem starts growing, the the amount of time to do one iteration remains much slower. Let me go to the computations. I'll show you the computations. That way you can get a sense. There is one thing that I need to add here. We have an assumption that all the value functions that we approximate are non-negative. If it is not non-negative, we push the functions up to make them non-negative. So as long as there is a lower bound that we can estimate, we can push the values of the functions up to make them all non-negative. And once you make them non-negative, then you can do this kind of an approximation over iterations. So I'll leave that for you to look at the details. I want to just go straight to the computations and show you what happens with the same instances. So here is an instance which is a battery storage instance. I'm, um, I'm sure you've heard of battery storage instances in stochastic LPs. Warren loves them too. So anyway, these are hard problems. And so if you look at it, there is a 14 node problem, there's a 30 node problem, there's a 57 node problem. Okay. So you take a look at time per iteration for SDDP. This side is all SDDP. You take a look at time per iteration, and as you go down, as the number of nodes go up in the network, the time per iteration starts increasing. If you take a look at time per iteration on this column here, it remains pretty stable. Okay. In other words, because the number of because the we keep the number of runs in the forward pass and the backward pass limited to just one, it doesn't blow in the number of in the amount of time taken per iteration. And if you look at objective function values, you still get about the same kind of objective function values. You see, you have 20, you take a look at every row, 6530, 6537, 6346, 6353. They're off by a little bit, they're not quite off that much. In other words, by using this more of a nonlinear optimization structure, you're able to go beyond smaller instances and enlarge it with the amount of time being. So basically, we did some statistical tests on the value function values, and you they're indistinguishable from the statistics that you see. But what you do get is an advantage in the speed with which it runs, and therefore you can solve larger instances. That's basically the takeaway from this. All right, so let me see if there is any other point. There are other instances as well, the same thing that you will notice that the growth isn't as much. Let me work on this summary, and the summary is that we use the state variable formulation, which is just a little more in tune with things like MATLAB. Computational results in terms of quality are comparable with SDDP, but the time required is far less, and it scales on bigger problems much better. There is one other thing that is not listed on this talk, which is the creation of policies. Creation of policies doesn't have to be just for this. You can use the same kind of policy creation for SDDP as well, which is essentially look at the dual bases that show up on the backward run. Don't throw them away, because that will help create the policies that you need to approximate out of sample questions. Now, in SDDP, they don't worry about out of sample because the whole sample is assumed to be given. we have to worry about the outer sample because we don't know. But this helps for operational purposes. When you go to operate the system, you have a policy that's available to you at the end. Okay, it's 2 o'clock. I'm going to stop right here. I'm sorry, I think I ran over.
Thank you very much. No, we arrived at 5, so we finished exactly on time. Uh, I mean, maybe one short question. If
Okay.
someone has a question, we can take one. So again, either through the chat or raise your hand. So I don't see anyone raising their hands or asking a question. If not, I will say thank you, Professor Sen, for this very nice double talk, in a sense, the two talks.
Well,
One
I
that
was
was
just
added at a bit, just short of the hour. But thank you very much. It was quite interesting, very interesting. So it concludes the talks for today.